Hello, good day everyone. So today you're going to learn about the instrument called Atomic Absorption Spectrometry AAS. This instrument is for the chapter 2. So here is the list of content, okay, the overview of the subtopic, the topics. So for the first 2.1 is about the principles and instrumentation of AAS and also AES. Okay, so as you can see, there are two different instruments. The first one is atomic absorption spectroscopy, and the other one is atomic emission spectroscopy. Okay, so for 2.2, it's about the application of AAS, basically widely used in wastewater detection. Okay, and the next is 2.3, tells about the interference of AAS. So we go for the first point in order to understand more about the AAS. The first point is atomic absorption spectroscopy involves the study of the absorption of radiant energy by neutral atoms in the gaseous states. So basically, this kind of instrument required a source of energy, and from this source of energy, it will absorb the energy. Okay, I mean the molecule will absorb the energy, and this process occurred in the gaseous state. Okay, so these atoms are in the ground state. So basically, all of the analytes are in the ground state, and it is not a radical state. Okay, so basically, it's already in the ground state, and the molecule are in the stable condition. Okay, and basically when we talk about spectroscopy, we are talking about the Beer's law. So I hope that most of you already learned about Beer's law in the analytical chemistry. Okay, so basically when we talk about AAS, we are focusing on the source of energy. Okay, so basically when we look at the source of energy, this kind of instrument, they will change or they will atomize. Okay, they will atomize our analytes, okay, and other component in the matrix, okay, to become atoms, okay, or a free gaseous atom. Okay, so basically all of the sample are commonly in the liquid form. Okay, so basically from the liquid form it will change to the gaseous phase. Okay, so this is what we call as atomization. Okay, and between there are different between molecular and atomic absorption. So that's why it need to be converted to a free atom. Okay, and in this kind of instrument, there are two methods of atomization. The first one is flame atomization, and the second one is electrothermal atomization. The difference between flame atomization and electrothermal atomization is the source of the energy. So as you can see that for the flame, they use a flame, the real flame, okay, and for the electrothermal, they use the plate, okay, the hot plate that can they atomize all the sample, okay, uh, become atoms. Okay, so when we talk about the conversion of from the liquid form to become the atoms, okay, so atoms will absorb the radiation. Okay, so by the time it absorbs the radiation, uh, there is only electronic transition will take place. Okay, so basically the atoms will be transferred. okay, to a higher energy level. Okay, that is the common process that occurred in the atomic absorption spectroscopy. Okay, so what is electronic transition? Okay, this is the transition of an electron between two orbitals or energy levels. Okay, so I believe that most of you already know and understand that the transfer of electron from low energy to higher energy does require an absorption of energy. Okay, so by the time this electron going from the higher energy to lower energy level, so this is can transmit and what we call as a photon. Okay, okay, so in this case, when we talk about the absorption of energy, line spectrum can be observed. Okay, so this is the basic concept of atomic absorption and emission, just like what I tell you just now. So in the A, for this part, this is the process of absorption of energy from flame, furnace, or plasma. And for B, this is the emission of energy. By the time it emits energy, uh, it will give a signal. Okay, it will give a signal as a photon. Okay. Okay, so what is the difference between emission and absorption? You can see clearly from this schematic arrangement of instrument for AAS and AES. Okay, so for emission, you can see that the flame, okay, will burn your sample. So it means that your sample is not, you cannot get back your sample. Okay, it will be a flame. Okay, it will be burned. Okay, and after that it will pass into the monochromator. Okay, what is the function of monochromator? This monochromator is to choose the best wavelength in order to give a high signal. Okay, this monochromator is the one that function to choose the lambda maximum. Okay, so after that it will pass into the detector. Whereas for the absorption, okay, so you can see that it must have the source, okay, and the sample will burn, okay, in the flame, and the same process after that, okay, it will pass into the monochromator and go to the detector. Okay, so the difference is in absorption, they require another source, okay, they require another source to to give another energy to give more energy towards atoms, okay, and then you can see very clear the signal, okay, after passing through the okay, next is the so this is the schematic arrangement for the AAS. Okay, so basically when we talk about AAS, it does require a light source. Okay, so this light source will provide a certain amount of energy to the atoms. Okay, the atoms that produce in the flame. Okay, so in order to burn the samples, okay, or to convert from the liquid sample to atoms, it does require one compartment which we call as atomizer. Okay, so atomizer is some kind of burner, okay, that make the flame uh, to burn the sample. Okay, and after that it will pass into monochromator, and then at the end it will go for detector. Okay, so here for the exercise, okay, we're looking at the notes. Draw a schematic diagram for an atomic absorption based on the description below. Analyze from the sample was excited using flame, and then measurement of one wavelength was collected. Okay, so basically you need to remember or memorize, okay, the schematic diagram of AAS is very important. Okay, try to draw it. Okay. Okay, so now let's look for the light source. Okay, now we go for from one compartment to another. Okay, the first one is what we call as a light source. Basically, we use the hollow cathode lamp. So basically, this kind of light source, okay, it will have what we call as the positive charge and negative charge there to give what we call as a current to supply the electron, and there is an anode and cathode there. Okay, and surrounded by the neon filled gas. Okay, so basically the why we choose neon, because neon is a stable gas and it will not become radical when we give supply certain amount of energy. It will still considered stable. Okay, and then we have also the quartz window. So basically quartz window is a very strong kinds of element that can be used as the cover. Okay, and the penetration of the energy, okay, from the light source, okay, it will not affect the analysis. So that's why we choose quartz as the window. So next, when we look at the process of the hollow cathode lamp, the first one is ionization. So basically, the neon gas will be ionized, okay, and then it will form the neon plus, okay. And next is what we call as sputtering. Okay, in this process, you can see that the neon, the positive neon, the positive charge of neon gas. Okay, it will go to the cathode and anode. Okay, and then the metal will going out. Okay, it will going out to become to enter the gas phase. Okay, and then the next part is what we call excitation. So from the metal, okay, so from the surface of the metal, it will become a circle of excited metal. Okay, and then we go for the emission. So from the excited metal, okay, it will uh, undergo the emission process and it will form a photon. Okay, because when there is a process of emission, it will produce some kind of energy as a photon. Okay, so this light or photon will be measured then. So next we go for the atomizer. So what is the function of atomizer? The atomizer is to convert the sample into atomic vapor. So basically, we always have the liquid sample, and then from this liquid sample, it will undergo the atomizer and to become the atoms. Okay, to produce the atomic vapor. And in this atomizer, flame atomizer, okay, it does consist of nebulizer, mixing chamber, and also burner. So here is the schematic diagram of AAS. Okay, so you can see that from the resonance lines source, okay, so it will undergo the flame atomizer. Okay, and here is the nebulizer. It's like a pistol. Okay, so this is your sample. It will suck the sample, and then when it comes here, then it will become mist or uh, in a small, very tiny particles of size. Okay, so after that, when there's a lot of solution, okay, in here, then it will go to the waste. Okay, so here this is oxidant gas. Okay, so this is what we call as spray chamber. Okay, and after that, this after it becomes the atom, then it will go on. After it become the small tiny particles in here, it will go on to the flame, and it will become the atoms. Okay, and after that, it passing through the monochromator, and in this monochromator, it will passing through many lens, and after that, it will go to the detector and amplifier. Why we use amplifier? Because certain analytes cannot be detected at very low concentration, so that it does require an amplifier to make the signal bigger. Okay, so after it passing through detector and amplifier, so it will go as an output. Okay, so basically for AAS, it will give you the value of the absorbance. Okay, the absorbance of the your analytes. Okay, okay, so this is what we call as the burner or atomizer. Okay, so here you can see from the sample, this is the nebulizer assemble. So here you can see this is the spray chamber. Okay, so at this stage, your sample is not atoms yet. Okay, so at this stage, your sample is in a mist form. Okay, very tiny particles of liquid. Okay, and you can see there's a fuel and oxidant. So this is the function of this is to make your liquid sample to become small. I mean to become small in particles. Okay, and very tiny particles. Okay, and once the spray once the spray if the spray is not good enough, it will go to waste. Okay, so after that, by the time the spray is good, then these tiny particles of liquid sample will passing through the burner head. This is what we call as burner head, and this is the optical path. Okay, so here you can see the burner head. This at this part, this is the flame comes out. Okay, and then your sample also will comes out here, and then your sample will get burned. Okay, and after that, your sample, your very tiny particles of liquid solution will become the atoms. Okay, now what is actually atomization? Okay, so by the time the liquid sample is sucked through a capillary tube, okay, by a high pressure stream of gas flowing around the tip of the tube. So basically in this process, it will require a very stable gas like nitrogen gas or neon gas. Okay, so so these are actually very important in order for the AAS to be worked out. Okay, so next is the sample is converted into a fine mist. Okay, so just like what I mentioned just now, the fine mist here is we refer to the small droplets of solution. So this at this stage, it must passing through the nebulizer. Okay, and the sample is aspirated into spray chamber. Okay, the impact of the sample with the glass impact bead produce aerosol mist. Okay, this is the part that I mentioned just now, that it will become a fine mist. Okay, next, the aerosol mist mix with combustion gas. Okay, so it will mix with the combustion gas like from the fuel. Okay, So this will, after that it will pass into the burner. Okay, so at the burner the combustion occurred. Okay, so at this stage the fuel and oxidant is like the source of the combustion process. Okay, and after that the burner will vaporize the aerosol particles and it will form the gases, molecules, ions, and free atoms. Okay, so this is the things that we need. Okay, to passing through the monochromator and after that through the detector. Okay. Next, the annular atom absorbs the radiation from the light source. Okay, so that's why you can see there the absorbance is directly proportional to the concentration. So from this relationship, you can see that it obeys the Beers-Lambert law. Okay. Okay, so here we can see that for the flame atomization, what kinds of flame we produce. Okay, so basically they will use a mixture of air and acetylene gas. Okay, so air acetylene flame with a temperature of about 2300 degrees Celsius. Okay, or the nitrous oxide with the acetylene flame. Okay, so it's a mixture. Okay, so it will depends on various analysis. It will depends on the analysis. Okay, and the sample required very high temperature or at optimum temperature. So basically, we will have about 2300 degrees Celsius for air acetylene flame, and for nitrous oxide with acetylene flame, it does require about 2700 degrees Celsius. And next is for the drying process. The solvent is evaporated and the dry sample nanoparticles remain. Okay, so basically at this stage, they try to remove the solvent. Okay, next is vaporization, is to transfer the gaseous phase. The solid particles are converted into gaseous molecule. So at this stage, it will transfer from liquid to gaseous phase. Okay. Okay, for the atomization, you must remember there are different between vaporization and atomization. That for the atomization, you must remember that the molecules are dissociated into free atoms. Okay, so it doesn't belong to gaseous phase anymore, but it will refer to the free atoms. Okay. Next is ionization. So for the ionization, depending on the ionization potential of the analytes. Okay, so basically it will depends on the kinds of the kinds of the sample. Okay, to ionize the liquid sample. Okay, to become gaseous ion. Okay, so now let's look for the electrothermal atomization. So basically, when we have the electrothermal atomization, we will use graphite tube. So why we use graphite tube? As you all know, graphite is comes from the element we call as carbon. Okay, graphite. So when we talk about carbon, we can say that the graphite tube is a very stable uh, compartment. Okay, so that it will it can be the electrothermal as a source. Okay. Okay, so now in graphite tube we have drying. Okay, to make to evaporate the solvent. We have pyrolysis. So this is the stage that most of the metric constituent will be removed. And next is atomization, where your analytes of element is released to gas phase, and after that cleaning. So basically, we use um, uh, some of the residuals. Okay, will be removed at high temperature. So by the time we want to clean the graphite tubes, we will use very high temperature to clean uh, the graphite tube. Okay, so this is the schematic process of atomization when we use thermal. Okay, so here you can see that we have various stage of um, uh, species. Okay, like we have excited state. Okay, we have a vapor state. Okay, so here we can see the molecular will become the molecular vapor and atomic vapor and also ionized atomic vapor will be at equilibrium. So at this stage, we can consider that the process is at the equilibrium state. Okay, so you can see that after it's undergo the aerosol spray, then dissolution, and then it will become vapor, then it will reach the equilibrium state. Okay, then when it reach the equilibrium state, you can see it will produce a certain amount of energy called photon, and this amount of energy can be determined as a signal. Okay, so next we talk about the nebulizer selection. So basically when we want to choose nebulizer, we will choose the stainless steel. Okay, because stainless steel uh, can at high temperature it will still consider as a stable. Okay, so that's why we choose stainless steel. Okay, and we also can use platinum. Okay, so basically when we use platinum, we can use very I mean the concentration of acids. Okay, so next is corrosion resistant plastic. So basically we will use a very concentrated acids. Okay, like for the aqua regia and HF. Okay, so this is the process that the things that we will use. Okay, um, as a nebulizer. Okay, so now we go for burner head selection. So at this for the burner head, the burner head must be about 10 centimeter head or 5 centimeter head. Okay, so it depends on the what kinds of the mixture of gas as a flame. Okay, so for 10 centimeter, they will use a mixture of air and acetylene flame. For 5 cm heat, basically they will use nitrogen acid, nitrogen oxide, sorry, nitrogen oxide gas and acetylene flame. Okay, so in order to choose the burner head, okay, so you must consider the following criteria. Okay, so the first one is allow to pass through highly dissolved solids without blockage. So basically, at the burner, okay, before we pass into the burner, we must pass into the what we call as nebulizer. So at this stage, you must make sure that there is no blockage occurred. Okay, in the nebulizer. Okay. Next, made of stainless steel or titanium to avoid corrosion. Okay, this is the reason why we need to use a very stable element, okay, as our burner, because at high temperature or very high humidity, uh, we can avoid the corrosion from happen. Okay. Next, the construction of burner depends on the oxidant fuel gas mixture to prevent the flame from flashback. Okay, so the construction of burner is very important because if the the construction is wrong. So the flame can be flashback. Okay, can be, I mean, can be uh, not work out. Okay, so this is the reason. Okay, to prevent the flame from flashback. And then so you need also to consider the 5 centimeter head, okay, of measurement for nitrogen oxide acetylene gas as a flame. Okay, so now we have a what we call as a commonly used fuels and oxidants. So you can choose, okay, which are the fuel and oxidants and what is the temperature range that you want to use. So basically, when we have a very high temperature range, so you can choose the mixture of acetylene and oxygen. Okay, so this is the commonly used of fuels and oxidants in AAS. Okay, so basically we use the um, acetylene air. Okay, acetylene air mixture. Okay, of a fuel oxidant, and the temperature range is 2100 until 2400 degrees Celsius. Okay, so when we talk about acetylene flame, so basically we refer to the analytes, okay, that can absorb at less than 200 nanometer. Okay, so in this mixture, there are possible chemical interference. Okay, there is always interference occur in the even in the instrument. Okay, next the nitrous oxide acetylene. Okay, so this is higher temperature. May cause ionization interference. So this kind of fuel and oxidants. Okay, it can cause ionization interference. And next are useful for elements that tends to form heat stable refractory oxides. Okay, so if your elements or analytes, okay, that can form tend to form heat stable oxides, so you can use this kind of combination of fuel and oxidants. Okay, able to overcome chemical interference in air acetylene flame. So when we have a high temperature, so basically we can avoid the what we call as chemical interference. Okay, so what is a monochromator? So you can see. So now we go for monochromator. Okay, so what is monochromator? Monochromator is an optical device that separates polychromatic lights, okay, into a range of individual wavelength and allows a narrow band of this individual wavelength to be selected. That is what we call as monochromator. And then from this slide, you can see that the function of monochromator, okay, that comes from the flame, okay, it will passing through the flame, and after that, it will go into the entrance slit, and then in this monochromator, there's a lot of lens, okay, and then it will go towards this exit slit, and then at this stage, individual wavelength has been chosen, and then it will passing through the detector. Okay, so now the light detector. Okay, so basically we use the photomultiplier tubes. Okay, and from the lights, I mean from the source of the lights. Okay, okay, so here you can see this dynode, and here is anode. Okay, so basically you must know that when the lights is transmit, there's an electron in this light. Okay, so it will passing through the photocathode. Okay, and then go passing through the dynode, and the last stage is anode. And then from this at this stage it will convert to a current. So now let's look for the application of AAS. So basically we have two kinds of analysis. The first one is qualitative analysis. So this AAS can be used to confirm the presence of suspected elements. Okay, and the second one is quantitative analysis. So we can simply prepare or construct a calibration curve, okay, based on the standard solution prepared, and this is what we call as an external standard method, okay. And also we have another calibration method called as standard addition method. So basically we have the various kind of value of concentration of our analytes, and we must consider, okay, the concentration when we use AAS. So the concentration of element basically in unit milligram per liter, okay. So this kind of concentration required to produce a signal of 1% absorption. So what we can understand from 1% absorption, 1% absorption is equals to 0.0044 absorbance. Okay, so this is actually a very tiny of a signal that we can detect by using AAS. Okay. So in the linear working range, okay, so basically when we prepare the standard solution and we run using AAS, we need to determine the range, okay. So the characteristic concentration can be determined by reading the absorbance produced by a known concentration, okay. So we can calculate the characteristic concentration, okay. So by using this formula, okay, equals to 0.0044 times concentration of standard divide to absorbance of standard. Okay, so for example, is the AS is the best working condition if a 6 ppm iron standard gives 0.12 in absorbance. So you must take note the characteristic concentration factors. Okay, so in this case, um, if the characteristic concentration is about like 0.11 ppm, so we can consider as AAS is in the best working condition. Okay, now we go for the application of AAS. So we go for the detection limit first. Okay, detection limit or limit of detection is the same. Okay, so what we can understand from this detection limit is the smallest amount of an element which can be detected with a reasonable certainty. So basically the detection limit will be 3 times from noise, okay. So this is what we call as a detection limit. So next, there are factors that affecting optimization. So we can consider the size of the droplet. So in the nebulizer, because the smaller size, the better evaporation rate and the better atomization. If the size is bigger, so the process of evaporation will be difficult, and in some case, the vapor will not passing through the the head burner. So when it doesn't going through the head burner, so there is no potential for your analytes to become atoms. Okay, so that is the problem. Second is choice of fuel and oxidants. Okay, if you want to detect like iron, okay, so you must consider what kinds of fuels and oxidants that are appropriate for your analysis. Okay, does it require a very high amount does it require a very high range of temperature for a flame? So when you have lots of interference, so you are advised to have a higher temperature range. Okay, so you need to choose wisely your fuels and oxidants. Okay, and next is another one is a choice of solvent. So basically, there are many kinds of solvent. We have organic solvent, and from this solvent, you must know that uh, there are certain solvent that are not easily to be evaporated. Okay, so it is advised to choose the solvent that are very light in formula weight and easily to be evaporated. Okay, so for the sample preparation, in order to obtain the sample in the form of solution, okay, to obtain the sample in the form of solution. So basically, sometimes there are samples that comes to you in a solid form. So you need to or you need to dissolve first your solid sample to become liquid form. Okay, because AS will only work out if your sample in a liquid form, okay, in a form of solution. Okay, so for insoluble solids, what you can do, you can digest with strong acid. Okay, you can use the aqua regia. Okay, you can use HF as the strong, like a very strong acid. And next is to concentrate samples. Okay, you can simply concentrate your samples using the liquid liquid extraction. Okay. Next, okay, the final part of AAS is the interference of AAS. Okay, we have five different interference of AAS. Okay, we have metric interference, chemical interference, ionization interference, spectral interference, and also background absorption. So what we can say about metric interference, okay, so you can see when you have like 1% of nitric acid and 5% of sulfuric acid, okay, so you can just passing through this nebulizer, okay, and then you can see that the droplet size is vary. Okay, so you can see that the metric interference is actually comes from the viscosity properties. Okay, metric interference is caused by the viscosity and the surface tension effect. Okay, the surface tension parameters. Okay, so here you can see that this matrix interference can be reduced. Okay, if you consider the uptake rate, the droplet size, and also the sensitivity. Okay, so here the most important is the uptake rate. Okay, so now we go for the chemical interference. So basically, chemical interference occur when the sample contains a thermally stable compound, doesn't atomize. So basically, there are certain element is not easy to be atomized due to the thermally stable, okay, properties. So here you can see that the numbers of atoms in the flame capable of absorbing light is reduced. So when this occurred, so you can see that the absorbance also will be reduced. Okay, so for example, the phosphate reacts with calcium ions to form calcium pyrophosphate in the flame. So in this case, you can solve this problem, okay, by adding high concentration of platinum or use nitrous oxide as the lean flame. Okay, so now we how we can overcome the chemical interference. Okay, so the first step is to remove interfering anion. Okay, by separation technique. You can use the solid phase extraction. You can use a liquid liquid extraction. It depends on your sample. Okay, and your analytes. Okay, next is use a hotter flame. So when you have a hotter flame, you can have a higher temperature. Okay, so this also can overcome the chemical interference. Next is addition of releasing agents like lanthanum strontium, salt. Okay, so this is what we call as a releasing agents. Okay, next is addition of protective agents like EDTA or 8-hydroxyquinoline. Okay, so these are protective agent or so called as a masking agent. Okay, so they can try to they I mean you can try to use any kinds of agent in order to avoid the chemical interference being detected. Okay, so now we go for the ionization interference. So what is the ionization interference? So this kind of interference occurs when the flame temperature has enough energy to cause the removal of an electron from the atoms to become ions. Okay, so basically it is require a very high temperature to make it ionize. Okay, so as a result, it will produce a very low absorbance. Okay, signal. Okay, there are many ways to overcome the ionization interference. So you can use excess of an easily as an ionizable element like potassium, sodium, okay, to the blend standards and sample to suppress the ionization of analyte. Okay, we can try to ionize the our analyte. Okay, use a cooler flame, but chemical interference may result. So by the time you make the temperature become lower, so it will invite the chemical interference. So you need to choose wisely what is the solution for your problem. Next is the spectral interference. So this kind of interference occur when an absorbing wavelength of an element which is not your analyte present in the sample falls within the bandwidth of the absorption line of your analyte higher than actual absorbance. So this is a spectral interference, also we call as a ghost peak. Okay, so when there is a ghost peak redundant on your analyte's peak, so it will make your absorbance peak to become higher. Okay, so this is something that we are you should know how to overcome. Okay, basically, when multi-element lamps are used, the slit width normally used with single-element lamps may allow an absorbing wavelength of another element to pass through. So basically, even though you use the single-element lamps, okay, so still you can detect the quite similar elements of your analytes. Okay, I mean they are the elements that quite similar to your analytes. Okay. Okay, so how we can overcome? This can be overcome by using a smaller slit or selecting another wavelength. Okay. So when you have a smaller slit in the monochromator, so it is better, okay, in order to overcome the spectral interference. So now what is background absorption? Okay, so there are two causes of background absorption. The first one is light scattering between particles in the flame, and the second one is absorption of light by undissociated molecular forms of matrix materials in the flame. So basically these two causes can cause the background absorption happen. Okay, so by the time there's a light scattering occurred, okay, so it will give like a higher signal of absorbance. Okay, and also when there's a undissociated molecular forms of matrix materials also will contribute to a higher absorbance signal. Okay, so how to compensate this problem? It is by install a continuum source like uh, H2 gas arc lamp or deuterium arc lamp in the optical system to measure background absorption. So from this, the continuum radiation from the D2 lamp is passed through the flame alternately with the hollow cathode beam. Since the atomic lines are very narrow, so the D2 lamp is mostly absorbed by the background, whereas the hollow cathode radiation is absorbed by the atoms. So here you can see that the background absorption can be solved, okay, by using the continuum radiation like D2 lamp, okay, deuterium gas lamp. Okay, by comparing the radiant power of the two beams, the atomic absorption can be corrected for any background absorption. So okay, so thank you very much for your attention, and I hope you can try to understand this the whole for chapter 2, and that's all for this chapter 2. Thank you.